Honey is the only food that can last for 3,000 years in an Egyptian tomb without spoiling. Yet it often turns into a rock-hard brick in your pantry within a few months. This transformation isn't a sign of spoilage or because the manufacturer added cheap sugar. It is a sign of chemical purity. The reason honey crystallizes involves a specific conflict between two sugar molecules and a state of matter known as supersaturation. Knowing this process changes how you buy, store, and eat this ancient sweetener. To understand the rock-hard jar in your cupboard, you first have to look at honey's basic composition. It is a supersaturated solution where bees have managed to dissolve more sugar into water than is physically stable at room temperature. A typical batch consists of roughly 80% sugar and only 18% water. In a standard chemistry lab, that much sugar would naturally fall out of solution and sit at the bottom of the beaker. Bees prevent this by using enzymes to break down flower nectar, but the laws of physics eventually win. The solution always seeks balance by trying to eject the excess sugar to return to a stable state. And that ejection process is what we see as crystallization. Not all sugars behave the same way, and honey is primarily a conflict between glucose and fructose. Glucose is the difficult one because it has a much lower solubility than fructose, meaning it separates from water much more easily. When honey crystallizes, the glucose molecules separate from the water and latch onto each other to form glucose monohydrate crystals. Fructose is more soluble and tends to stay liquid. The specific ratio of these two sugars determines the fate of your jar. If the glucose levels are high, the honey will turn solid rapidly. But if fructose dominates, it might stay liquid for years. If you are finding this explanation helpful, consider subscribing to the channel as we break down the science of everyday questions like this every single week. We can now examine why some honey stays liquid forever. This glucose to fructose ratio depends entirely on which flowers the bees visited. This is why a jar of rapeseed, dandelion, or clover honey will almost always turn solid within weeks of harvest, because these plants produce nectar that is naturally rich in glucose. Honey varieties like acacia, tupelo, and sage have unusually high fructose content. Acacia honey can remain perfectly clear and liquid on a shelf for years because the glucose concentration is low enough that it never reaches that major tipping point for crystal formation. When you buy generic wildflower honey, you are getting a mix of nectars, so the crystallization speed is a random chance based on what was blooming near the hive. Expensive raw honey from the farmer's market turns solid much faster than the plastic bear from the supermarket because crystal growth requires a starting point known in chemistry as a nucleation site. Raw honey is full of microscopic particles like pollen grains, bits of beeswax, and propolis. Each of these tiny specks acts as a seed where glucose molecules can anchor and begin building a crystal lattice. Large commercial brands often use a process called ultrafiltration, which forces honey through high-pressure filters to remove every trace of pollen. This removes the nucleation sites and keeps the product liquid on the shelf longer, but it strips away the distinct local qualities that define raw honey. One specific scenario exists where crystallization can ruin your honey due to water displacement. When glucose crystallizes, it drops out of the solution and leaves its share of the water behind. This causes the remaining liquid portion of the honey to become more diluted, rising from that stable 18% water content to something much higher. If this water activity rises enough, osmophilic yeasts naturally present in raw honey can activate and start consuming the sugars. This creates fermentation. If you open a jar of crystallized honey that has separated into a solid bottom layer and a runny top layer that smells sour, it has likely fermented and should be discarded. Keeping honey in a cool, dark pantry is often considered the best preservation method. But 14 degrees Celsius, or 57 degrees Fahrenheit, is the worst temperature for storage. This temperature range accelerates glucose crystallization faster than at any other point. If you store honey below 10 degrees Celsius, the viscosity becomes too high for crystals to form effectively. And if you store it above 25 degrees, the crystals dissolve. The pantry often sits right in that rapid crystallization zone. Freezing honey stops the process entirely without damaging the nutrients. But it makes the honey impossible to pour. Most experts recommend keeping daily use jars in a warm spot in the kitchen, rather than a cool cupboard. When your honey turns solid, you can reverse it, but patience is required to protect the chemical integrity. The goal is to melt the glucose crystals without destroying the enzymes like invertase and diastase that make raw honey special. The temperature limit is 40 degrees Celsius or 104 degrees Fahrenheit. Heating honey above this point begins to degrade these enzymes and increases the levels of hydroxymethylfurfural, a compound used to indicate heat damage. The safest method is a warm water bath. Submerge the glass jar in warm water rather than boiling water, and let the heat transfer slowly. Never use a microwave because they create hot spots that can boil microscopic sections of the honey, which destroys its raw properties and nutritional value. Crystallization is not always a nuisance because sometimes it is the goal. Beekeepers have developed a method to control this process, to create creamed or whipped honey. This is not honey with dairy added, but rather honey that has been forced to crystallize rapidly using a specific seed crystal. By introducing very fine microscopic crystals and keeping the honey at that ideal 14 degrees Celsius temperature, beekeepers force the glucose to replicate those tiny crystals instead of forming large, gritty shards. The result is a product that is solid but spreads like peanut butter. It is the same chemical substance as the liquid version, just organized into a different physical structure that remains stable on the shelf. Do not throw away a jar of honey that has turned solid in the back of your cupboard. That change in texture proves you bought a real natural product that is behaving exactly as chemistry dictates by moving to a more stable state. Whether you choose to melt it back down or enjoy the crunch, you are seeing a process that has happened in beehives for millions of years. If you want to understand the science behind other pantry staples, make sure you are subscribed for our next breakdown.